Hi everyone. Last time we talked about orders of reaction for a reaction that only has one reactant. Today, let's determine our rate law when there are multiple reactants. So really we're determining the order of the reaction. So in this case, again, we would have two or more reactants and they're becoming products. And remember that the concentration of the reactant is related to the rate of our equation or reaction. So changing each of the reactant concentrations will affect the overall rate of the reaction. So in order to determine the order here, we're going to change the initial concentration of one reactant at a time. And then we're going to see how that affects the rate. In your textbook, there is an example problem, and in this problem, we're going to consider the reaction between nitrogen dioxide and carbon monoxide, and that produces nitrogen monoxide and carbon dioxide. So the products don't necessarily matter here because we're just interested in the concentration of each reactant and then the initial rate. So let's say that the initial rate of the reaction is measured at several different concentrations for each of the reactants, and the tabulated results are shown here. From that data, let's determine the rate law for the reaction and the rate constant for the reaction. Okay, let me just grab my notes. And of course my dog is sleeping on my notes. Okay, there we go. So to start, let's figure out what the order for each reactant is. So we've got our set of data here, and we can see that we've doubled the concentration of our first reactant. So let's see how that affected the initial rate. And notice that the concentration for carbon monoxide did not change during these first two sets of data. So if we look at the initial rate, that has quadrupled. So that already tells us that the order for NO2 is 2. Because remember, if you double the reactant concentration and the rate quadruples, that means N is equal to 2. So we can already start to write our rate law here. And now we just have to figure out what the order is with respect to carbon monoxide. So in the next set of data, we can see that the concentration of carbon monoxide is doubled, but the concentration of NO2 is held constant. So let's see how the rate is affected here. So nothing really changed, maybe a tiny bit, but it's negligible. So there's no change here. So what that tells us is the reactant concentration has no effect on the rate of the reaction. And remember, that refers to a zero order reaction. So I'm going to change that X to a 0. Okay, so now that we know the order for each reactant, the overall order of this reaction is just 2, because if we add together the orders for each reactant, we get 2. So that's the overall order. All right, so now in part B, let's determine the rate constant for the reaction. So to determine the rate constant, we are going to rearrange our rate law to solve for K. Now, keep in mind that anything we plug in for carbon monoxide is raised to the power of 0. So that's just going to equal 1 no matter what we do. So really, we can narrow down the rate law to K times NO2 squared. And now we can rearrange for K. So K should equal the rate divided by NO2 concentration squared. And then we just pick a set of data to plug in. So let's just pick our first row. So let's just plug in the rate, which was 0.0021 moles per liter per second. And then we'll divide that by the concentration of NO2, which was 0.1 moles per liter squared. And then if we plug that into our calculator, we should find a value of 0.21. But what about our units? So the units for this constant are always going to be a little bit tricky. So we have molarity in the numerator and then molarity squared in the denominator. So one of those will cancel in the denominator, but we'll still be left with 1. So we'll have m to the negative 1. And then seconds doesn't cancel, and it's also in the denominator. So we'll say seconds to the negative 1. So you're going to see some pretty funky units here for the rate constant. But that is our answer for B. Okay, so now let's work on worksheet problem 3. And this is a pretty similar problem to the example problem. So if you do want to work on this on your own first, feel free to pause the video. But let's say we have some data for a reaction between CH3Cl and chlorine gas, and then we don't really care about the products in this case. So my table format is a little strange. I picked a weird table to use, but we have the concentrations of both of our reactants in the first 2 columns, and then the initial rate in the last column. So let's write an expression for the reaction rate law and calculate the value of the rate constant K. What is the overall order of the reaction? So let's compare the first 2 sets of data, and we can see that the concentration of the first reactant is doubling, but the concentration of the second reaction stays the same. Now let's see what's happening to the rates as a result. So that looks like it is also doubling. And so that tells us that the order in regards to the first reactant is 1, because the initial rate is doing exactly what the concentration is doing for the first reactant. So they're directly related to each other. So let's just start writing out our rate expression here. We'll just put a 1 there. And then the other reactant, Cl2, and we don't know what the order of that is, so we'll try to figure that out. Okay, so now let's look at the second set of data. So we can see that the concentration of our second reactant is doubling, while the first reactant concentration is held constant. And then what's happening to our rate? It's not really double, but it's also not staying the same. It's kind of somewhere in the middle. So maybe we should use that method that we saw earlier, where we're going to compare two rates and two concentrations. Okay, so I'm going to compare two sets of data here to figure out what the order is with respect to chlorine. All right, I'm just going to pick these two sets of data here because we saw a change in the concentration for chlorine. And we didn't see a change in the concentration of our first reactant. All right, so the second rate was 0.041 moles per liter per second, and the first rate was 0.029 moles per liter per second. And then we have K times the concentration at time 2 there, and that's over K times the concentration at time 1. All right, so the ratio of the rates, let's see, so that ends up being 2.07. Let me just double check. Oh no, sorry, that's 1.4. Looking at the wrong notes there. And then we'll set that equal to, let's see, what's 0.1 over 0.05? So that is 2. All right, and then that's raised to the power of n. So now let's take the log of both sides. And remember, we can move the n value down when we take the log of 2 to the n. All right, so now on the next slide, I'll continue this calculation. So we have the log of 1.41, which is equal to n times the log of 2. So to solve for n, we have log of 1.41 over log of 2. And that will give us a value of 0.5. Okay, so remember I told you before that sometimes we don't have whole numbers for the order of a reaction. Sometimes we can have fractions or decimals. So the rates here is equal to K times the concentration of CH3Cl to the power of 1 times the concentration of Cl2 to the power of 0.5. Okay, so the overall order for this reaction is, let's see, I'll write this over here, is 1 plus 0.5, so that is 1.5. All right, and that can happen. It looks a little strange, but that does happen. Now we also need to figure out the rate constant K. Oh, I didn't leave myself enough room here. We'll just do that up above then. Okay, so we need to solve for K, so I'm going to rearrange that equation that we just wrote. So K is equal to the rate over the concentration of our first reactant to the power of 1 times the concentration of our second reactant to the power of 0.5. So we can choose really any data point. Let's see, I'll just choose the first row of data. So the rate is 0.014 moles per liter per second divided by 0.05 to the 1 power, and then multiplied by 0.05 to the 0.5. And our units overall in the denominator will be m to the 1.5, which is a little strange, so we'll narrow that down later. Okay, so we should get a value of 112. And if you want to double check my work, please feel free. And then in terms of units, we have 1 m on the top and 1.5 on the bottom. So we'll end up with m to the negative 0.5 and s to the negative 1. So remember I told you the units for rate constants can be pretty tricky, and as you can see here, it's a little strange, but that is how that would work out. Okay, so hopefully this helped a little bit with determining orders of reactions and also determining rate constants for reactions. And I will see you in the next video.